So in the previous video, we looked at deriving the formula for the charge on a capacitor. Capacitor, resistor, or a resistor, capacitor, or RC circuit. Being that it was a long, complicated process and made some mistakes, right, and so on. And would have put some amount of stress on the brain. I'm going to do a revision of what we did earlier. All right, so you have R dq by dt plus q over c equals v. And remember, this is current, the rate of flow of charge with time, dq by dt multiplied by resistance. We call current time resistance, right? And that's the resistance, the voltage drop across the resistor. Q over C is the voltage drop across the capacitor. And both of them add to get the applied voltage, total voltage. So now, here, you see that this takes the form of a differential equation. The general form is dy by dx plus py equals q, and the integrating factor is e to the integral of p dx, right? When I leave this a looking like d, this d looking like a is p dx. All right. So here now, dq by dt, when we divide by r, dq by dt plus 1 over rc times q equal v over r. So our p will be 1 over rc, and our q, I use a different q from this, would be v over r. So integrating factor is equal to e to the integral of p, which is 1 over rc, dt, because we're using dt instead of dx here. When you integrate 1 over rc with respect to t, you have 1 over rc by t, same as t over rc. So the integrating factor is e to the t over rc. Alright? You multiply both sides by the integrating factor. You have e to the t over rc times the left hand side dq by dt plus, then you have 1 over rc times q and multiply by e to the t over rc. I rewrote it as 1 over rc by t, but for consistency I'll put it back as t over rc, right? And then equals e to the t over rc times v over r. Alright? Then we realize that what we have is a reverse product rule. This is a result of differentiating a product rule, the left hand side. And we compared it with the general form of a product rule. We saw that one product was q, that's what we differentiated here, I held here. And the other product was e to the t over rc, that's what we held here and differentiated here. So it's the derivative of e to the t over rc by q, and that is equal to e to the t over rc by v over r. Then we integrate both sides. The integral of the derivative with respect to t of e to the t over rc times q dt equals the integral of e to the t over rc times v over r dt. Now we rewrote it here. It's the same thing. Integral of d by dt of q e to the t over rc dt equals the integral of v over r e to the t over rc dt. Now when you integrate the derivative of a function, the function is left undisturbed, so we have q e to the t over rc dt. No, the dt wouldn't be there after you integrate. What we have is q e to the t over rc, alright? We have q e to the t over rc left alone, undisturbed, equals, we put v over r outside the integral sign, so the integration is less messy, less things to write in it. So that's e to the t. I rewrite it as the t over rc as 1 over rc by t to separate the constant clearly from the variable dt. So here the v over r must multiply the entire integral, right? I mistakenly left off the brackets earlier and did not multiply the v over r by the k. So I put the bracket here. When you integrate e to the constant t dt, we have e to the constant by t divided by the constant. In this case, the constant is 1 over rc. So e to the 1 over rc times t. When you integrate that with respect to t, you get e to the 1 over rc by t divided by 1 over rc plus the constant of integration. I use k instead of the common c here because I already have c to represent capacitance and I don't want to confuse them. Now q equal e to the t over rc. q by e to the t over rc equal v over r. I open the bracket and multiply both parts by the v over r. With v over r times, we divide by 1 over rc. So it's same as multiplying by rc over 1 e to the t over rc. But here r will cancel r. Plus v over r times k. So here now q e to the t over rc equals, now r cancels r, so I have c times v, that's cv, e to the t over rc plus v over r by k. Alright? So now we say that we divide both sides by e to the t over rc, right? What we have is that q equals cv e to the t over rc divided by e to the t over rc, and the e to the t over rc is cancelled, plus v over r times k over e to the t over rc. So what we get as a simplified form is q equals cv plus, now it's v over r times k e to the negative t over rc. As remember your indices, you divide by a number to a power, a positive power, is the same as multiplying by the number to the negative power. Alright? Now, initial conditions say that when t is 0, q is 0. So 0 equals cv plus v over rk e to the, when this is 0, it becomes e to the negative 0, same as e to the positive 0, but when you have a number to the power of 0, you get 1. So it's v over r by k times 1. That's what we have. So we use this to find out what k is. Subtract cv from both sides, we have negative cv equal this v over r times k. Multiply both sides by r, so we have negative cvr equal vk. Divide by k, we have negative cvr. Now we divide by v. Negative cvr over v equals k, and the v is cancelled, so k is negative rc. Now when we put it back together, q equals cv plus v over r k, but k is negative rc, so we put negative rc here, and put back the e to the negative t over rc. But r cancels r. So what you have is q equals cv, the minus sign here, I put minus here. R cancels r here, so we have c times v e to the negative t over rc, and then factor out cv. So what we have is this: q equals cv 1 minus e to the negative t over rc.